Hey everyone, welcome to Lubrication Experts. I've got a super exciting topic today. We're talking hydraulic oils, a very high volume product. You've probably all used a hydraulic oil or at least seen a hydraulic oil. So very excited to talk to someone who is very knowledgeable about the topic. So I'm going to introduce John Sander. He is from Lubrication Engineers. So it's the other LE, right? So I've obviously changed this brand to more of like an LX, but these are the original LE guys, Lubrication Engineers over in the US. So you may have come across them. Most of their specialization is that in that sort of industrial space. John is the Vice President of Research and Development, very knowledgeable chemist, so really excited to get his insight. He's been at Lubrication Engineers for over 30 years, a lot of experience that he's going to bring to the table today. So very excited to talk to John. John, thank you so much for coming on.
Rafe, you're absolutely welcome, and I'm looking forward to this as well. I've actually had some experience and exposure to some of the work you've done, and I'm very honored to be participating in that as well.
Oh, thanks. Thanks. So what we're trying to do here is just kind of like spread the gospel of lubricants. So um, one of the major focuses of that is obviously hydraulic oils because they're so prevalent across the industry. So maybe one thing that we could talk about, is just to sort of set the table, if you like, is where are hydraulic oils used? And are there any nuances to the applications that we should be aware of before we get into the discussion?
Absolutely. I think that's a great place to start because it develops a little background. And I think that's one of the challenges. You already mentioned the fact that it's one of the highest volume markets of lubricants that's out there, probably just behind engine oils. And one of the reasons why that's the case is I think part of the fallacy of how the hydraulic fluids are used. Oftentimes they're considered an inexpensive disposable product. And I think in the direction that you and I will lead farther in this conversation is that that's going to change. And part of that's driven by policy and just changes in how even consumers want to see sustainability and all those things looked at. But as of right now, oftentimes you'll see that a lot of hydraulic systems are not very well maintained. And as such, the fluid leaks out. And because it leaks out, it's not in the equipment very long. And therefore, the users don't want to spend a lot of money for it because they know it's not going to be in there very long. Therefore, if they were to have it in, put something expensive in there, they're throwing away expensive stuff they didn't really get to use. So it's very common for them to want to put the cheapest thing they have in there, let it spill out, maybe collect the stuff, maybe not. That's the scarier side, is in some plants it can even become a safety issue because of where the oil ends up. And so, like I said, I think you're going to see that. I believe industry is going to move in a direction that's going to favor a change, a new revolution, if you will, in hydraulic fluids and the philosophy of how they're maintained and used.
Yeah, that's really interesting that you say that because it absolutely mirrors my experience. And it is maybe a little bit industry specific, so I don't want to tar entire industries with the same brush, but here in Australia, for example, it's very common in the quarrying industry to treat hydraulic oils basically as a commodity, right? Or as a once through use product. There's almost an expectation that they'll spill on the ground, which from an environmental standpoint is not great, but it also devalues the product as well, right? Whereas
I
when you
agree.
go over to something like, I don't know, plastic injection molding, they seem to place a lot higher value on the product, a little bit more willing to treat the system with a little bit of due care and diligence.
That's right. And I've heard you say this once before, and it's completely true. I believe that these fluids or the lubricants need to be treated as an asset, just like the machine. They are actually a part of the machine. Now, maybe they don't last as long as the metal parts, but they are still should be treated with that level of importance. Yeah, I mean, we have our blood in our body, and we like to think of that blood as being part of us, and that's how you need to treat that oil as well. And so, if you don't maintain it and put crummy blood inside yourself, you're probably not going to be very healthy. And the same thing's true of your machine. Food industry is another one of those that's very specific, and they have very specific formulations and even requirements on those formulations that don't allow for just easy selection of what the ingredients look like and or how they might perform in certain applications. So uh, fire resistant hydraulic fluids, and there's a lot of industries that mineral oil is not flammable, but combustible. And therefore, if it were to spill out onto some of their hot type applications, say, for example, a um, steel plant, they may burn down an entire line because the hydraulic line blew off and sprayed oil everywhere. So you're right. There's got to be some level of difference that's already out there. And some of those markets are already familiar with having to pay higher dollars and buy a very specific type of formula to their application. But that's not true everywhere for sure.
Yeah, that's really interesting that you've already identified a couple of segments where hydraulic oils are maybe a little bit more niche or a bit more specific. So one which I find really interesting is the rise of, uh, well, they've always been around, but those fire-resistant hydraulic fluids, I'm seeing the conversation change around those a little bit. Now it's going a little bit further into, well, if we use something which is fire-resistant, can we go to our insurer and get a reduced premium? Because now we're reducing the risk of fire, explosion risk, burning down the entire plant kind of thing, which is an existential threat to the business, but also is a huge cost to the insurer as well. So I've seen that conversation change a little bit with some of the customers that I work with. Maybe just to step back one bit, because those are obviously very specific niches when we talk about formulating for the food industry as well as the fire-resistant fluids. But there's probably maybe a larger divide that we generally see in the hydraulic oils, which is mobile versus fixed plant. So in my head, the way that I always think about it is, okay, fixed plant, you don't really have as much of a space restriction. You can have larger oil reservoirs to cope with, let's say, for example, a giant industrial press. You go into the mobile plant side of things, and any extra weight that you carry is extra fuel that you've got to burn. And so we seem to be seeing this trend towards higher power densities, lower, much smaller oil reservoirs, higher oil temperatures, and things like that. And so while there's always been a little bit of a difference in the way that the hydraulic oils are used, that bifurcation, in my experience at least, seems to be getting bigger. But how do you see it?
I agree. I think there's absolutely more of a gap being formed, especially on a lot of the mobile equipment that you referred to. They're either getting larger. So you mentioned the mining industry, for example. I mean, gosh, that equipment just keeps getting bigger and bigger and bigger. Uh, but they're trying to also improve fuel economy, and and I guess in that roundabout way, that's trying to reduce the carbon footprint and some of those things that ultimately governments and consumers are really, really desiring these days. Even there's now even investment funds that are investing in trying to reduce your carbon footprint. And so I think that we're going to see more and more desire from like in the car and automotive industry, we're very seeing it with engine oils where you're seeing reductions in viscosity, higher use of synthetics, and therefore the cost of those engine oils has kind of continued to go up. Uh, that's starting to spill over into the industrial industry as well, because those vehicles, while they're considered work vehicles, they're starting to look at those and say, well, we got to reduce emissions. And the only way they can reduce emissions is to make them consume less fuel, oftentimes, especially the carbon emissions. Some of the other emissions, burning the fuel itself, that's a different thing. But if you can make the machine do more work with less fuel, now you produce less carbon emissions. Now, that having been said, I've also seen in the mining industry where they want to work the equipment even harder, because if I can move the same amount of soil or with less scoops of the earth, then I can get the job done quicker and more efficiently. Same thing with the big trucks that drive up and down and in and out of the mine holes. Those things, if I can put 10% more on the trucks that I'm driving, then I can send one less truck trip up and down out of that mine, and that's costs maybe millions of dollars a year.
This is probably maybe a good segue into the relation of hydraulic oils to hydraulic efficiency. Right. So we know that there is a link there, and there's been a bunch of studies done. Could you please maybe take us back to the fundamentals and explain how it is that the properties of the hydraulic fluid influence the efficiency of the hydraulic pack?
Sure. That's a great question because there's a lot of ingredients that go into the hydraulic fluid. So at the high level, I like to break it down and say, well, just starting out, there's two main ingredients. There's the base fluid and there's the additives. And so when you use the term base fluid, that then can be broken down into subsets. And depending on what it is that you use for the different types of base fluids, that can perhaps control, number one, what the cost of the product is, but number two, how it performs. And so you could start off with mineral oils. That's probably the most common still today. And those are refined from crude oil, sort of naturally occurring, but separated and created so that they perform quite well. They've got good lubricity and last pretty decently long. But they do come with some limitations at times. Because if you've got oxygen in those things present, which we do in the air we breathe, and the equipment that you have moving and agitating the oil, they can eventually wear out maybe a little bit faster than the second type of base fluid, which are called synthetics. Now, the term synthetic often is used like it's one thing, but it's actually a very broad term for a large number of different things. We talked about the fire-resistant hydraulic fluids. Those are something called oftentimes a phosphate ester or basically a regular ester. Those are commonly used, and some of those esters are even used for biodegradable type products because they do have some biodegradability properties. There are synthetics that are not biodegradable. Not all of them are necessarily biodegradable. There's PAO synthetics, polyalpha olefin. So that's why I say us formulators have a lot of different base fluids available to us. Interestingly, we talked about this fire-resistant hydraulic fluids. One other one that you might not think of a lot of times that's used as a base fluid is water. Water is not a very good lubricant, but it's actually a very good coolant. So one of the ways that you put out a fire is to cool down the heat. So they make fire-resistant hydraulic fluids that are actually water oil emulsions. And so what they do is mix together the oil and water, or even certain types of synthetic base oils, to provide lubrication, but also to keep everything cool and douse out a fire if it were to spray on it. So those are the various different base fluid types that we can pull out of our toolbox. Additives gets a little more into deep things. For example, you've got rust and oxidation inhibitors that can go into the product. There's anti-wear additives. Typically in hydraulic fluids, we'll be looking at either zinc, so ZDP, zinc diethyl phosphate, and there's various different versions of those. And even picking the right one of those can have some effects on hydrolytic stability or even the anti-wear properties and how it matches up with some of the other ingredients in there. But there's also ashless or phosphorus containing ingredients that are used typically for anti-wear as well, and some sulfur containing ones. There's rust inhibitors to help protect. So a lot of times we know when we think about lubricants and hydraulic oil specifically that we put them into lubricate, but one of the things that you don't think about with lubricants is all the other things that they do, and especially hydraulic fluid. I would actually say that lubrication is probably secondary in hydraulic fluid. The main job a hydraulic fluid has is to do work. So you're taking the fluid or taking some sort of chemical or physical energy and putting that into a pump that then pumps pressure to the fluid. And because you can take a small amount of pressure and the pressure is constant throughout the entire fluid, do big work with that same small amount of oil. So that's why hydraulics becomes so important to us in all those various different industries and mobile applications you and I were kind of alluding to. But as you can imagine, all those ingredients we put in there then have an effect on how the product flows back and forth in the hydraulic system, how it coats and protects, how it defends itself. Those oxidation inhibitors and things have to protect the oil because the oil is also removing heat from the application. So there's many different things that we know that the oil is actually doing aside from just what we call it a lubricant.
Yeah, that's really interesting. One thing I just wanted to pick up there when you were discussing additives, when you were talking about zinc, for example,
Yes.
there's a couple of different nuances that I always like to understand a little bit better when it comes to zinc. Obviously, it's I mean, probably by volume, the most popular additive in the world because of its presence in engine oils and hydraulic oils and all the rest of it.
Yes.
But one thing that we are starting to see with hydraulic oils is a lot of zinc-free hydraulic oils, and they're advertised as such.
Yes.
So, could you please help explain from, let's say, from a chemist's standpoint or a formulation standpoint, what's the decision point which drives you to a zinc versus a zinc-free formulation?
So there's actually kind of two decision points. For me, number one, so the zinc comes down to that I mentioned hydrolytic stability. Some of those zinc compounds actually can, if not chosen properly, hydrolyze. And what that means is if you get water into the system, it will actually start to break the molecule, for lack of a better description. So it doesn't do its job as well and starts to turn into kind of a sludge or debris inside the oil rather than lubricate. So that's number one. But secondarily, zinc has been also kind of pointed out as a bit of an environmental toxin if released into the environment. I say that, and it's going there all over the place, leaking out of people's crankcases in their cars, and even these leaky hydraulic systems. But they are at least trying to become a little more aware. I know, at least here in the United States, for example, they had what they call the Great Lakes initiatives. I assume you're familiar with the Great Lakes that we have up in the northern part of the U.S. and kind of in between the U.S. and Canada. And they had put some regulatory requirements in place for vessels that would be on the Great Lakes because they had seen that there was accumulation of zinc compounds that were in some of the fish that would be caught for food in the lakes. And they said, well, we've got to stop that. So a lot of times your environmentally friendly products will be non-zinc containing. There'll be more of that phosphorus direction. Food grade is one other place. ZDP is not approved for incidental food contacts.
Yeah, that's really interesting. And that's sort of one side of the coin. That's the downward pressure on reducing the amount of zinc in the
Yeah.
formulations. In some circumstances, there is the reverse, which is upward pressure to increase the amount of zinc. And I'm thinking specifically of the Caterpillar specs, right? You often are reading in the hydraulic oil specs must contain, 900 parts per million or more. What's the reason? Do you know what the rationale is behind that?
Yeah. So the interesting part about that zinc molecule, uh, kind of breaking down the name, zinc dialkyl dithiiophosphate. So the dialkyl, that's kind of what describes the difference from one zinc to the next zinc, is whatever that alkyl group, that's a common name for a bunch of chemistries. The thio means there's sulfur in it, and the phosphate means there's phosphorus in there. Both the sulfur and the phosphorus provide some level of wear protection and also a little bit of the activity of that compound. Not to get too deep into the chemistry, but there's what they call primary and secondary zincs. And I won't delve into the difference other than the fact that there is a difference. And you select those two also depending on what it is you're trying to accomplish. So temperatures can degrade one of them. Keep in mind that what you're trying to do is thermally activate these ingredients. When they're just sitting in the oil floating around, they don't do anything. But when you start getting metal surfaces in contact, it's that little bit of heat that starts to make these things become active and turn into the anti-wear additives that we want them to be. And it's honestly not the zinc in the molecule that's actually doing that. It's either the phosphorus or the sulfur portion of it that's providing that anti-wear. So going back to that, basically the Caterpillar spec does require that you're going to be putting in a higher amount of it. A higher amount of it will actually mean that there's more available anti-wear additives. And I've seen the same thing. A lot of race drivers, for example, will say, well, I need to have a 2,000 part per million zinc containing engine oil. And why? That's because they've seen that it holds up a little bit stronger. There's more chemistry available there, and therefore it's going to carry a higher load for a longer amount of time. Now, what's the negative of that? As that does break down, you're going to see it create more sludge in the used oil. So typically in engine oil, it's not a big problem because they've got a lot of detergents in there to handle it. Hydraulic oils, on the other hand, you want them to separate from water oftentimes. So you don't want to put in all of that, or else it won't be able to separate from water. If you put the detergents in there to suspend the sludge, you'll also suspend the water and then you won't be able to remove it. So you have to end up throwing the oil away sooner than you might want to.
Yeah, and that speaks to something we've spoken about on this channel. I think it was Jim Carey that talked about the difference between the automotive engine oil formulation and the industrial oil formulation. That idea that in engine oils they're sort of designed to carry all the crud that comes about because of combustion, whereas with industrial oils we don't really expect that so much. So that certainly explains a lot. Uh, could we maybe then, for some of our listeners who are going to be end users of the products and want to understand a little bit more about sort of decision making on the type of lubricant that they use, you talked about the production of sludge if we have
Yes,
a zinc content that's too high. And obviously, sludge and varnish can be produced as a result of base oil degradation and that kind of thing as well.
sure.
So when we're making decisions about what kinds of hydraulic oil we should be using, realistically, what kind of telltale signs in the equipment are we looking for? Something that would spring to mind would be the smaller the tolerances on your servo valves, for example. Now you're probably a little bit more concerned about silting, as well as the development of sludge and varnish. Is there anything else that we should be considering?
Temperature for sure. So a lot of these uh, ashless formulas can actually go to higher temperatures. And in fact, the interesting thing about that is and I find myself having to kind of back myself off a little bit because there's a lot of crossover between different types of formulas. So it's possible to use some of those same chemistries. We already found that we're using zincs in engine oils and hydraulic fluids. And in some cases, it may be the exact same zinc. But the same thing's true of the ashless chemistries. Some of those are used in air compressors and turbine oil formulas where over there, there's nothing at all that is in there to help manage degradation. I hate to call them lightly formulated, but they kind of can be because you put too many additives in there, then the base fluid can't carry the degradation of the additives, and eventually those varnish things you're talking about become a problem. Same thing being very true, just as you aptly started referring to, in a hydraulic system with very, very tight clearances. So I would see that an ashless product would be desirable in something like that, or perhaps even the ones that are high temperature. If they're very high temperature, the phosphorus only will tend to break down into less of a sludge than would a zinc containing material. There's an additive that I didn't talk about, and I think it's kind of important as we segue kind of in the direction you were headed here too, talking about how maybe the oils are distinguished between how a user might choose the right one. And that's viscosity index improvers. I really didn't talk about that, but I think it's important to point it out because the research you were talking about for energy efficiency, some of it has been dedicated to the viscosity index of the oil.
Mm.
And that can be formulated into the product either based on using a synthetic base fluid or by taking a mineral oil and boosting the viscosity index with synthetic polymers that they place in there. And those synthetic polymers adjust the viscosity index. What we're starting to look at that point is how does that oil flow amongst itself? Not only how is it flowing in the machine, but how do the molecules within the fluid itself flow amongst themselves and create fluid film friction with each other? I know it gets kind of complex to think about this, but that's really where you're starting to get when you're starting to look at these fuel efficiency studies. And we can lubricate relatively well from hydraulic oil to hydraulic oil. They're still pretty good lubricants. But when you're trying to really differentiate and try to see if you can improve fuel efficiency or energy efficiency, depending on what kind of equipment we're using there, electrically driven or fuel driven,
Mm.
the way that you can accomplish that is by decreasing also the friction within the molecules of the actual lubricant itself. And that's where a lot of these are going. The higher the viscosity index, they're finding the better fuel efficiency or energy efficiency you get because the fluid itself has less thermal eddies and maybe even the molecules slide past each other a little bit easier because of this sort of squashed down line of how the fluid viscosity might change with regard to temperature. So the viscosity plot stays flatter in a sense.
Yeah, interesting. So I think we're slowly building up to the full picture of hydraulic efficiency. just
Yes.
want to take one step back before we get there,
Okay.
because we're talking VI improvers, which are obviously a
Definitely.
very important part of the formulation. And I guess VI improvers have always been, certainly in the field, I think they're viewed as like the cheat code of viscosity index, right? So you can formulate one of two ways. I could go with a really uh, high viscosity index synthetic oil. You typically don't see a polyalkylene glycol in hydraulic oils, but a polyol ester or a really high VI PAO or something like that. Or I can get my cheapest, nastiest recycled base oil and just pump it full of viscosity index improvers, right? Now, obviously, there is a wide spectrum of formulations in between those, right? And I'm
Yes, there is.
sure that uh, my understanding is that the VI improvers have improved considerably over the decades. They're a lot more shear stable now than they used to be. But for the consumer, someone who's purchasing these lubricants, what are some of the things that they should be looking for that would indicate that, yeah, my product has a great VI, but that VI is actually going to stay there over time?
No, that's a fair question. And I don't think most of us marketing the products would ever publish exactly that. Well, my product has, I mean, we might say it in the verbiage that
Mm,
it's got high shear stability. Shear is actually one of the things that we know is a high probability within a hydraulic system. And that is one of the weak spots for some VI improvers. In fact, over the years on engine oils, engine oils, they always kind of sold the concept of shear being good and bad. So in diesel engines, they've typically always gone with a little bit more shear. And the idea there was they knew they were going to get a lot of building of viscosity based on soot loading.
mm,
Hydraulics, that's not the case. Hydraulics, if the oil shears down, then it becomes thinner. Thinner then makes you begin to worry, okay, well, if it's thinner, am I going to be providing the same film strength and therefore increasing wear? That can be true if you choose a real shear unstable VI improver. But for most applications these days, they are kind of picking a sweet spot. If you really want to, I say they, I know at least we are. We try to look for that sweet spot where what you'll find is the more shear stable the VI improver is, oftentimes the less they build VI. So you can really pop the VI up like crazy with a real shear unstable VI improver. But
mm.
if you put a very shear stable one in, it doesn't shear, but it doesn't move your VI that much. So it's kind of like you have to find an in-between place where it's got good shear stability, but also good viscosity index building.
Mm.
And it does kind of give you that happy medium of being able to control price a little bit of the final lubricant, but also to provide that beneficial performance that I think the end user is going to want. I think if somebody doesn't give any kind of nod at all to saying that my formulation is shear stable, that should be a flag. The end user should probably ask their lubricant provider about that. Say, worried, is your product shear stable? And if they stutter and don't really answer the question, I would probably say you might want to move on.
Yeah, yeah, interesting. All right, so I think that's been really helpful because we've sort of built up all the components of the hydraulic oil now. We've talked about the base oil and the additives and some of the decisions that you can make around that. When it comes to the picture of hydraulic efficiency,
Yes.
I've always seen that chart which maps volumetric efficiency against mechanical efficiency, and you're trying to widen the window by using the viscosity index. Are you able to just explain or elaborate on that a little bit further and explain how is it that the properties of the fluid can affect, I guess, the shape of that chart?
Basically, that is what they're looking at, is trying to figure out how do I make that fluid flow more efficiently through the system? Because you keep in mind that it's traveling various different turns, and some of those, depending on how the system was designed, whether it's having to make 90-degree turns or trying to smooth out the turns, the smoother it is, the more efficiently the product flows. But largely what they're finding too is that you start getting warm spots. If the oil has any kind of place where it struggles to flow,
Mm,
you get warm spots in there. With increased VI, that means that for some reason, I think the way the molecules line up in the product, it tends to flow through those struggle spots a little bit easier. And
Okay.
so therefore, as a result of that, that's when you're starting to see more efficiency because the molecules in the oil itself are moving past each other more efficiently.
So maybe the question, if I can phrase it a little bit better, would be that flow that you're talking about, those flow characteristics, is that contributing to the volumetric efficiency or to the mechanical efficiency, or both?
I believe it's a little bit of both,
Mm,
uh, but they do talk a lot about the volumetric because basically trying to get the fluid where you need it as fast as possible. And that tends to also result in mechanical efficiency in the
okay,
end.
interesting. All right.
And see, the other thing that's been, I think, really noticeable is that if you have your high VI products, they typically don't tend to take on air as much. Air can be a problem because air restricts the flow, increases the temperature, it makes the system spongy, and so any of these high VI products typically seem to have a lot better air release properties. And as a result of that, they don't create foam, and basically that allows for that volumetric efficiency. Because that you can imagine that affects your volume if you've got a lot of entrained air in the product. And in some cases, the operators will complain about what they call sponginess. And
Yeah.
that sponginess is often due to entrained air being present in the oil, which also, once again, affects that volumetric flow efficiency within the entire system.
Yeah, that makes a lot of sense. Ah, interesting. It's nice to see how all the different components come together. So as we sort of start to wrap up here, I always like to end these interviews with a view to the future of what does this market look like in the next 10 to 20 years. And I know everyone's got a different version of their crystal ball. Mine tends to be wrong most of the time. Um, in your view, where you see the market going, where do you see the big trends? You just see continuation of some of the trends that have been present for the last 10 years. So we're looking at higher viscosity indexes, slightly lower zinc, things like that. Or do you see other innovations on the horizon for hydraulic oils?
I actually kind of do see some higher innovations, and more specifically, just I don't think on the hydraulic fluid side of things, there's been as much opportunity to take advantage of the synthetics.
Mhm.
I think that's going to somewhat naturally occur just because of what you're already describing, that shear stability thing, as well as even the desire to create green products. And green can mean various different things for hydraulic fluids. Early on, when anybody mentioned the term green or a sustainable hydraulic fluid or an environmentally acceptable lubricant, uh, they usually just meant that it was a product that would be biodegradable. Well, it turns out that for biodegradability, you could either choose vegetable esters, which is, you know, regular soybean oil or something like that, but those products didn't last very long.
Mhm.
Today, they've figured out that we can make pretty high performance products out of what some of these products that are now biosynthetics. There's some of those that are out there. Unfortunately, they're expensive, and most of the users really haven't quite embraced them yet. But I think the time will come that regulatory pressure begins to press down on the end user saying, well, you can't lose this stuff unless it's biodegradable. And maybe even better yet, they'll start getting pressurized for bio-based. We want it to be renewable per se. And so these types of base stocks, they are both of those things. They're bio-based. But so that's one little trend I think could happen. But I also think just trying to increase your energy efficiency, improve the longevity of the application to continue to operate. So as we try to go for extended drains, I think that's another thing that's going to be considered to be sustainable is lower amounts of waste disposal. So all of those things together just really start to steer more towards the use of synthetics. To your point also, you were talking about the shrinking size and the ever increasing requirements placed upon these fluids to do more work, more with less, I guess, in a sense. That's just more of a desire to go towards synthetics. You know, and we're really seeing a lot more push for safety as well as environmental. It's that whole sustainability thing, how social responsibility, financial responsibility, and finally that environmental responsibility.
Yeah, that's really interesting. And previously on this podcast, we had the guys from Biosynthetic Technologies come to talk about some of their estolide formulations. Most of the time, we were talking about it in the context of engine oils, but we do know that they've been doing some work in the sort of the gear oil and hydraulic oil space. And I guess from what I understand, the weakness of the vegetable based oils was always that you could really only get them in low viscosities, right? I mean, cooking oil
Yeah,
is pretty thin, and so you're always having to boost them with like a PIB or something to increase the viscosity to anything that was sort of usable. Whereas with some of these um, newer biosynthetics or bio-based lubricants, I don't know clearly what the distinction is there. Maybe that's another podcast. Yeah, you can start to build up to larger molecules that have that sufficient viscosity to be practical for hydraulic applications.
yeah, I agree. And I think that's, well, I think maybe one of the reasons why they haven't taken on. So just tell you about our own line. The direction we went was we decided, well, we're going to roll out an environmentally acceptable lubricant line, and so we chose one of the variants of a biosynthetic base fluid that's out there. And basically, in the end, this stuff performs like a PAO. The challenge you have is that it's priced higher than a PAO. So you've now formulated this product that most people have already equated the EALs, or the environmentally acceptable lubricants, as being something that doesn't last very long because they're used to the vegetable oils. I'm going to put it in there. And while part of why you chose that is because you want it to last long in the machine, but you don't want it to last long in the environment. Well, those are diametrically opposed. If it's not going to last long, it's just not going to last long. But these biosynthetics, they're bio-based, and so they still have somewhat of an ester property to them to where they're biodegradable, but yet they also have been zipped up to be oxidatively stable. And so these things can perform at the level of synthetic. We rolled it out strictly as an EAL, and honestly, we're just not selling very much of it. I don't know whether the market's not mature for that, or whether it's just because by the end they were priced high.
Mhm.
So in retrospect, I think it would have made a lot of sense to have actually sold it as a synthetic hydraulic oil. And oh yeah, by the way, they're also environmentally friendly.
Yeah, there's definitely
Like,
that customer education piece that needs to go along with it, right? And you're right. Maybe as an industry, we're not pitching these correctly, and it's actually well, actually, these are high performing synthetics, but you're also getting the advantage that it's a green product, and that makes it
yeah,
even more appealing than a standard synthetic.
I mean
Um,
that's the funny thing to think about is you try to think of, well, what's the super hydraulic fluid that you could create out there? And in my mind, I envision this thing, and I think it's actually plausible. You could actually come up with something that's uh, approved for incidental food contact, so it's H1. It's biodegradable, it's bio-based, and performs pretty well. You could
mm,
do it. Now, it's not going to be inexpensive. That's the challenge.
yeah, that's really interesting. Well, John, thank you so much for sharing your knowledge. I am aware that we just skimmed the surface of hydraulic oils, and we could go much deeper on any number of topics because, as we said, hydraulics are present in just so many applications. So I'm definitely getting you back for another one of these. But it's been a pleasure, and thanks so much for coming on.
It has been a pleasure for me as well, Rafe. Thank you.